All right, last of the review. So this is going to cover pretty much week 3, a little bit of week 2 as well. And then, of course, week 4 for us was all review. So everything here this week is review. All right, anion gap. Anion means it has which charge? Negative. So if it has a positive charge, I am a cation, right? So that's the difference. So anion is how much negative stuff are we missing? So all I gotta do is add up all your positive stuff and subtract all the negative stuff. So there you go, 140 minus 105 minus 22, easy enough. There's about 13 milliequivalents per liter of negative stuff that we're missing. So for B, here I put them in the same order, positive, negative, negative, so it makes it easy. But just be wary, 130 minus 92 minus 13, that they might give you these numbers, these ions in a different order. So don't get complacent and just do subtract, right? Like for this example, I gave you an anion, a cation, then an anion. Just recognize, put the positive stuff here, and then subtract your negatives. Okay? Same thing with D. I put the cation here. So just be careful. You shouldn't end up with any negative because it's a gap. Right? There shouldn't be any negative numbers in your final answer. If you have one, just double check. Gram molecular weight. So this gives us a lot of information. So grams per mole, and it tells you also the exact number of molecules. All right, 6.02 times 10 to the 23rd. So if I measure out this many grams of this substance, I know I have exactly this many molecules. So for oxygen, we got 16 plus 16 because it's O2. So 32 grams. If I measure out 32 grams of O2, I know I have this many molecules. If I measure out this many grams of O2 at STP, it's going to occupy 22.4 liters, right? So that's how these numbers tie together. Carbon dioxide, we have 1 C and 2 O's, so we'll add the 12 for carbon to 16 and 16 for the 2 oxygens, 44. So use the figures in your book and round to the nearest tenths when you're using these. So 1 decimal place. All right, so a little more complex, but these are simple. There's no parentheses involved, so we just do them the same way as A and B. So carbon, we have 6 of them. Carbon we have 6 of them. Hydrogen, we have 11, and oxygen, we got 5 of them. So same, now we just have 3 different atoms to contend with. Now when we do D, this is telling you you got 3 of these. So you're going to have to multiply everything within that parentheses by 3. So technically, I would have C3H9, right? But that doesn't give me any structural information, so they write it in parentheses. But for us, for counting the atoms, we'll just distribute this subscript. So within the parentheses, there's 3 carbons, and 3 times 3 is 9 hydrogens. So the complete count, carbon we have 3 here plus 1 more for 4. Hydrogen we have the 9 here plus 1 more for 10. And that 1 lone oxygen. All right, so now we know the gram molecular weight. We'll use it for gas density. So at STP, 1 mole of gas will occupy 22.4 liters. So we're assuming we have a mole of this gas mixture. For A, 10% carbon dioxide, 90% oxygen. So it is the weighted average. So we're going to take the gram molecular weight of CO2 times its percentage, 10%, and then we're going to add that to oxygen's times its percentage, 90%. So let's see, CO2 from the previous slide, 44 grams, oxygen 32, helium, we got 4 grams per mole. So for carbon dioxide, 44 times 10%, so I changed the percentage into a decimal, so I don't have to worry about percent signs. And we're going to add that to the weighted average for oxygen. So oxygen is 32 grams per mole, and 90% comes out to 0.9 as your decimal. Don't forget to divide. So we got 10% plus 90%, that's 100%, which is 1 mole. So 22.4 liters. So make sure you do everything in the parentheses, do the addition, everything in the numerator before you divide by 22.4. So you should end up with 1.48 grams per liter. For B, same, right? We got a 70% helium, 30% oxygen, right? So this is helio-oxygen mixture. So we'll use this mixture in the future, right? Or we did it when we adjusted for helium-oxygen gas. All right, 4 grams for helium at 70%. Add that to 32 grams per mole for oxygen at 30%. And then don't forget to divide by Avogadro's number at STP, 22.4 liters per mole. So that comes out to about half a gram, 0.55 grams per liter. Now when you have 3 gases, you just repeat it. You just have an extra term in the numerator. So just continue on. If you have multiple gases, just continue adding them in the mixture. So for nitrogen gas, the only thing we didn't do for the previous slide, so nitrogen is 14, but N2 is 28. So we got helium at 4 grams, 5%, nitrogen gas, 28 grams, 75%, oxygen O2, 32 grams at 20%. So that comes out to about 1.23. NH3, so we got ammonium. So that's 14, 15, 16, 17 for NH3, 17 grams per mole at 4%. Nitrogen gas, 28 grams per mole at 60%. And O3 this time, ozone, 48 grams at 36%. So make sure you simplify everything in the numerator before dividing. Come out to 1.55 grams per liter. So another instance where Avogadro's number plays, that mole. Concentrations. So different ways for concentration. So alcohol by volume, we have weight for volume, volume for volume. But our concentration is going to be molarity. Right? The concentration we'll use, and this is going to help us determine pH, right? Because pH is the negative log of your acid concentration. And the acid concentration we want is in molarity, not percentage, not weight for volume. We want molarity. Molarity is moles per liter. So all I gotta do is solve for how many moles and then divide that by the volume. So we got 25 grams of salt, regular table salt, in 1.5 liters. So we gotta figure out how many moles 25 grams is. So first thing we got to do is figure out how many grams per mole. Right? So sodium is 58.5 grams per mole. So we take the 25 grams that we have, we divide it by the grams per mole, and that'll give us the number of moles. So we have about 0.43 moles. Once we figure out the number of moles, we just divide by the volume. Okay. So 0.43 moles divided by 1.5 liters. Just simplify that, and that'll give you your concentration, moles per liter, which is molarity. And that is a capital M. For B, we'll do it the same way. First, we got to figure out the gram molecular weight for potassium chloride. Right? So potassium chloride is 74.6 grams per mole. We have 100 grams of this. So if you're doing a low sodium diet, then they're going to make you use potassium chloride as your salt substitute. So 100 grams of salt substitute, 74.6 grams per mole. We have 1.34 moles. But molarity is per liter. Our volume they gave us in ml. So we just need to convert that to half a liter, 0.5 liters. So moles per liter gives you molarity. So 2.68. So that's pretty concentrated. Super salty.
So wait, the A to get 58.5, that's, you got that with periodic table?
Yeah, so take the weight for sodium, whenever that equals. Take the weight for chloride, add them together, and you'll get 58.5. Yep. So find your moles, divide by liters. Yeah. All right, we got some sugar, C6H12O6. So sugar has a gram molecular weight of, I believe, 180. Yep. So sugar is 180 grams per mole. So we have 375 grams of sugar at 180 grams per mole. And then all you do is divide by your liters. So about 0.42 molar sugar concentration. D, we got 50 grams, looks like bicarb, in 750 ml. So already off the bat, you know that needs to be turned into liters. How many grams? So we got ozone, 48, plus 12, plus 1. So that gives us 61 grams per mole. We got 50 grams of that stuff, divided by 61 grams per mole, gives us moles. And then we change the mLs into liters. Just divide.
It doesn't matter that that is a negative.
Oh, the ion?
Yeah, the ion. That's not good.
Yeah, it doesn't matter. So this is just saying what it is. So sugar has no charge. This guy just happens to be negative charge. Pressure conversions. So you're going to either multiply or divide. And the first thing you want to do is probably get into ATMs first. So ATM is like your middleman, your middle unit. So if you change everything to atmospheres, you can go to any other unit from there. So all of our conversion factor is based on the atom, 1 atmosphere of pressure, which is equal to a column that is 766 millimeters of mercury, or a column that is 1,032 centimeters of water. Conversely, it's also equal to 14.7 pounds per square inch and 101 kilopascals. Right? So just different units. Torr is the same as millimeters of mercury. So anytime you see a torr, you can just say millimeters of mercury. So the first thing you want to do is go to ATMs. Right? That's your first thing. Go to ATM. And then you're going to multiply or divide by the conversion factor again to get to your desired units. Right? So we got 0.66 atmospheres about, right? Save all your decimal places in your calculator, and if you have a memory function, use that as well. Because now to go to PSI, all you got to do is multiply by the conversion factor. And if you want to go to kilopascals, all you got to do is multiply by the conversion factor. So PSI, multiply by 14.7. Kilopascals, multiply by 1.101. So you end up with 500 torrs equal to 9.7 pounds per square inch, equal to about 67 kilopascals. So first step, divide to get into ATMs. Then your second step, multiply to get into your desired units. So here we divided, then we multiplied. All right, so first step, we gotta get to ATMs. So millimeters of mercury. So step one, we're gonna divide by the conversion factor, in this case, 760. Step two, we're gonna multiply by the conversion factor. Pounds per square inch is 14.7. Centimeters of water, 1034. Okay. So divide, right, by your conversion factor to get to ATMs, and then you multiply by your conversion factor to get to pounds. Right? 5%.
You got 850. Wouldn't you divide 850 by 760?
Yeah, right here. It's in the denominator, so you divide. So these are fractions. So we're simplifying fractions here. So this is conversion if you're following the units. That way the units cancel out and you're left in your desired units, pounds per square inch. So this is the long way with the units. So I used a shortcut the previous time. This is the long way for those who are following the units, so you know how the math works. So doing it multiple ways. Follow the one that's easier for you. So I'm giving you options. That's what life's about. Bam. So the units cancel out. You're left in PSI is what you want, 16.4. So I'll do the same for the centimeters of water, right? So start off with your starting point, put it over 1, and then just use your conversion factors. Make sure your units cancel out, and you're left with the units you want. In this case, water. It's about 1,156 centimeters. So, does it make sense? Yeah. So this is a little bit more than 1 atmosphere. So your pounds per square inch should be a little bit more, and your centimeters of water should be a little bit more than an atmosphere. Just a conversion exercise. That's all this is. Pounds per square inch. First step, divide by 14.7. Then for kPAs, multiply by 1.1. For atmosphere, divide by 14.7, and then multiply by, oh, you don't have to multiply, you're done. So do this step first. Pounds per square inch, you got 50. There's 14.7 pounds per square inch per atmosphere. And then every atmosphere, there is 101 kilopascals. So if you just do this step here, it gives you atmosphere. Bam, 3.4. So if you're following the units, it helps if you don't know when to multiply or divide. Avogadro's number. So we alluded to this in previous, but for gas laws, we'll definitely need to use moles. So number of moles equals a constant times your volume. 1 mole at STP, so ideal gas law, occupies 22.4 liters of space. And 1 mole is 6.02 times 10 to the 23rd molecules. All right, so let's figure out how many moles is in 800 liters. So it doesn't even matter what gas it is. We're just going to assume every gas behaves ideally. So all we're using is the liters. So which mole number gives you liters?
22.4.
So all you do is divide, right? 800 divided by 22.4. Grams. Ooh, now this does come into effect which gas it is, because we need the gram molecular weight. So nitrogen is 14, N2 is 28. So we got 65 grams, 28 grams per mole. So just divide. So about 2.32 moles of nitrogen gas. Oxygen. Does the gas? Yes, it matters because it's grams. So oxygen is 16, O2 is 32 grams per mole. So 200 grams of O2 gives us 6.25 moles. But do we want moles? What is the answer looking for? So don't stop here. Make sure you answer their question. So, which number do we want for liters? Are we going to multiply or divide? All right, let's set it up. I got 6.25 moles. I divide by 1. This is my conversion factor. I want moles at the bottom. 1 mole is 22.4 liters. So that's just a conversion. So you multiply. Multiply or divide. It's multiply. So multiply by the conversion factor. 22.4 liters, you get 140 liters. So this is a 2-step conversion. Molecules. Now we're using scientific notation. If you want to write out 24 zeros, be my guess. If you want to write out 23 zeros, be my guess. Okay. So we're going to divide. We're going to divide this many molecules by that number. So you're going to subtract exponents. Right? When you divide powers of 10, you're going to subtract exponents. So this is what the setup looks like. You can punch it in your calculator if it has exponents. If not, just subtract. So what you'll do is let me do it up here just in case I did it already. 8.3 divided by 6.02 times 10. 24 minus 23 is 1. So 10 to the 1 is how much? 10. And there it, you're done. So do 8.3 divided by 6.02 times 10, and you're done. So that should give you 13.78 moles. But we're not done, right? We want liters. So get your moles, multiply by Avogadro's number. So 309 liters. Yeah, I probably rounded. Ideal gas law. So we have to use Avogadro's number. For us, we're just going to use this R value. So your R value determines on your units. Our units are atmospheres, mLs, and this is the big one. So you have to be in mLs, moles, Kelvin. So the first thing is change your units into their desired units. So atmosphere is good. Liters, no, we need mLs. Temperature, we need Kelvin. So let's make those changes. Bam. So we got our atmosphere, 1.5. Our volume, 4 liters is 4,000 mLs. Our R value, our constant, 82.1, since we're in our desired units. And 70 degrees Celsius is 343. Right? All you do is solve for n. So you divide both sides by these two numbers, right? So the right side cancels out, and all you gotta do is simplify that term. Bam, right? So just simplify this term, because this and this cancels out. So you got about 0.21 moles. Not too bad. Okay? So here, just make sure you're in your desired units. Do we want pounds per square inch? We want ATMs, right? So we got to divide by 14.7. We don't want liters, we want mLs. So we got to multiply by 1,000. Moles are good, but our answer is going to be in Kelvin, which means we have to convert to Celsius because our final answer needs to be Fahrenheit. So this is going to differentiate probably a B from an A on the final. No laughing, that's just the truth. All right, so first step, change your units. So we got atmospheres here, 30 psi's divided by 14.7 gives you your atmosphere value. Your volume in mLs, 2,500. Your N value, in this case moles, is 4 moles. And then we have your R value. K, remember, it's going to give us K. We're going to have to go to Celsius and then Fahrenheit. So to get K by itself, we're going to divide both sides by 4 times 82.1. So K gives us 15.5. So to get Celsius, we have to subtract 273. All right. And then to go to Fahrenheit, you got to plug and chug it into the equation. So here's our Celsius value, plugged it in there, and then we solve for F. So you get negative 431.5. So when you go through the final, do all the easy ones first, and then go back and work on the more difficult ones. One last one for smiles and giggles. So remember your units. We want to be in atmospheres, mLs, moles, and Kelvin. So here we got Fahrenheit. We had to change to Celsius, right? 232.2 Celsius, and then we have to add 273 to get to ultimately Kelvin. So here it's the same problem, it's just we did the conversion for temperature on the front end. From now on, it's plug and chug. So we got to divide this by 101. So atmosphere, 243 kilopascals over 101 times your mLs equals your moles, your R value, and our temperature K. So about 98 liters for this volume, gas volume. Combined gas laws. So this is your starting equation for all the gas laws. So if you can remember, PV over T equals PV over T. Initial condition equals final condition. You should have no problem. Because Boyle's law, all the other ones, all they're doing is they're eliminating either temperature, pressure, or the volume variable. So here we're doing all 6. Get the hard one out of the way. It's just plug and chug. But you have to be in like units. For here you can pick any units you want, they have to be the same, and temperatures must be in Kelvin. So let's convert these figures, temperatures and pressures. So T1 becomes 277 K, P1 becomes that many atmospheres, and T2 becomes 293 K. So you had to do 3 conversions before you can plug and chug. Alright, so CC is the same as an ML, so we're in like units there, so we're good. ATMs, we're good. So we can just plug and chug. P1, V1 over T1 equals atmosphere, P2, V2 over T2. Now you just solve for P2 by multiplying by this reciprocal, right? So if you multiply both sides by 293 over 200, you'll get rid of that term. 293 over 200. Do that to that side, so I got to do it to this side. 293 over 200. So all you got to do is punch this in, all in one shot. 200 divided by 101 times 500 times 293 divided by 277 divided by 200. Right? The reason you divide here because it's in the denominator. You should come up with about 5.2 ATMs of pressure. Second example for combined gas laws. Again, getting the units you need to be in. So for temperature, we want to be in Kelvin. And for atmosphere, since the answer wants to be in ATMs pressure, we'll be in ATMs here for pressure as well. Liters and liters, they'll cancel out. So we're happy there with volume. From here, it's just plug and chug. So we'll plug in our values. So we got P1, V1, T1. P2 is what we're solving for. V2, T2. Again, to get P2 by itself, we multiply both sides by this reciprocal. 322 over 4. And we multiply this side by the same thing. Right, this cancels out, this cancels out. And then you just need to simplify the left side of the equation. So to enter it, 150 divided by 760 times 3 times 322 divided by 355 divided by 4. 0.13 atmosphere of pressure. That's about right. All right, Boyle's law. So PV over T. So for Boyle's law, the only thing they're eliminating is the T value. So PV equals PV, right? So if you start with the combined gas law, remove the T value, then you're left with Boyle's law. So you don't have to memorize all of these equations, just one to remember. So same thing, instead of 6 values, here we're only going to work with 4. So make sure your units are the same. Here we got torr and torr, they'll cancel out. Liters and liters, they'll cancel out. So plug and chug, 600 P1, 3V1, 850 is P2, and we're solving for V2. Divide both sides by 850, so you got about 2.12 liters for V2. For the second example, we got mLs and liters, which is easy to convert. Right? Just divide mLs by 1,000. Pounds per square inch, we need to divide by 14.7 to get it into ATMs. So 53 divided by 14.7 will give us ATMs, and 950 mLs is 0.95 liters. Now the units are the same. We can just plug it in and solve for V2. 1.14. Charles law. So PV over T equals PV over T. So in this case, there's no pressure. So they eliminated P. So you can do V1 over T1 equals V2 over T2. Right? So you can use these equations or this one. All right, temperature must be in Kelvin, so let's convert those. So T1, 323, and T2 becomes 303. Liters are the same, so they'll cancel out. Now all we gotta do is plug and chug. So T1, V2 is what we're solving for, T2, V1. So I'm just using this equation here. V2 is 4.69 liters. So the temperature went down. You would expect the volume to also go down a little bit. So this answer makes sense. One more for Charles' law. Let's change our temperatures. 311 Kelvin and 333 Kelvin, respectively, for T1, T2. And our cc's, which is the same as mL's, 0.8 liters. Using the same equation, plug and chug, and we'll solve for V2. So the temperature went up. We should expect the volume to also go up, and it did. It went from 0.8 to 0.86 liters. So the hotter it is, the faster they're moving, the more space the gases will occupy. All right, the last one, PV over T equals PV over T. This time there is no V, so it's just P1 over T1 equals P2 over T2. So we'll use this equation. Temperatures need to be in Kelvin. Here, our answer is in atmosphere, so we'll change torr to atmosphere as well. So you gotta do a lot of conversions in between. So plug and chug, P2, we'll isolate and we'll solve it. It becomes 0.32 atmospheres. One more example. So Fahrenheit, these are the ones it's gonna take a little more time, but just be careful. You guys should be able to convert to Kelvin easily. All right, we'll use this equation again, plug and chug, and P2 is 4.318. Let's see if that makes sense. So our temperature went down, so our pressure, went down a little bit. This is about 4.5. Speaking of helium oxygen earlier, when we had to find the density of the 70-30 helium oxygen, right? So what's the density of regular air? So remember, nitrogen is way heavier. That's 28 grams per mole. Helium, four. So that means, it's way less dense. So our gauges measures oxygen, right? O2, which is even bigger. Was that 32 grams? So our gauge is for oxygen. So this needle is reading oxygen. 0, 1, 2, 3, 4, 5, 6, etc. But we're not using oxygen. We're using helium-oxygen mixture. So we have to use a conversion factor. We're reading the gauge as if it's reading for oxygen, but we need to convert because it's not really oxygen, it's helium and oxygen. So 80-20, just multiply by 1.8. And then for 70-30, just multiply by 1.6 to get the actual. So the gauge is reading this, but what you're actually delivering is the final product. Reading 10, you're actually delivering 18. Reading 10, 70-30, you're actually delivering 16. So it's quite a bit difference and significant. So 80-20, remember to multiply by 1.8, and for 70-30, multiply by 1.6. So the only way you can goof if you interpose the factors. Just be careful. All right, cylinder durations, not too bad. We have H and K cylinders. Your conversion factor is 3.14. So this G here is the gauge reading. So whatever the gauge on the container is reading, every pound per square inch is going to give you 3.14 liters of oxygen. So let's figure how much is in the container and divide by the flow rate. So we have how many liters? So 1,000 pounds per square inch multiplied by the conversion factor will give us liters, and we just divide that by the flow rate. So that gives us about 628 minutes. Right, just round to the nearest minute. So for this one, same thing, 3.14 times the gauge reading divided by the flow rate, and that's liters per minute. I got lazy and didn't write minutes. 654 for that one. Let's see, duration. Well, it's just another example before we get into partial containers. So 3.14 times the gauge pressure divided by flow. So for D, we're not depleting the container. We're actually only going to use about 13 gauge pressure. So 1500 going to 200, so we're only using 13. So we'll use 13 to do our computation. So to get to 200, it's going to take 1,361 minutes, so about 22, 23 hours. E cylinders, a lot smaller. So the conversion factor per gauge pressure reading is only 0.28 liters. So for 2,000 at a flow of 4 liters per minute, you're going to get about 140 minutes worth. So these are tiny. B, 1,800 gauge pressure. And for these problems, we're assuming ideal conditions. You can use every last drop of oxygen. But in the real world, there is limits to how low the pressure can go. 84 minutes. Ooh. So short trip to the grocery store, that's all you got. Just convert it to liters. Yeah. Simple. Just divide by 1,000. All right. So for this example C, we're not depleting. We're going to 250. So we're actually only going to use 1550 of gauge pressure times the conversion factor divided by flow, which is 6. Ooh, even less. So you got to make a quick trip to the grocery store. And D, we're going to actually use only 1650 for D. At a rate of 5, 92 minutes. So not too bad. A little more, hour and a half. You can do a yoga session, hot yoga, 90 minutes. Would they survive with an oxygen tank? All right, continuing on. pH scale. So pH is measuring, of course, acid, and pOH is measuring base. But the relationship for us is, what do we get when we add acid and base together? Water. So our pH scale is based on water. So ours range from 0 to 14, 7 being neutral. So if you're at 7, you have equal amounts of acid and equal amounts of base. Low pH is acid, high pH is base. So the relationship, pH and pOH is 14. You add those together, always. So sometimes you'll need to find pH to solve for pOH, or sometimes you'll need to solve for pOH to find pH, right? So answer the appropriate question. So here we're looking for pH, pOH, we're looking for pOH. So the relationship is just plug and chug. Right? So take 14 minus 7.8, 6.2, right? So this number plus this number must always equal to 14. So if I have a pH of 0.3, my pOH would be 13.7. 0.3 plus 13.7 must equal 14. Right? So that's the relationship between pH and pOH. So pOH given now we're looking for pH. The math is the same. So this number plus this number must equal 14. 13.7, well, pH will have to be 0.3 in order to equal to 14. Always, because our pH scale is based on water. pH. So what is the actual pH number? Well, it's the exponent of the log base 10. And the concentration we want is in moles per liter, so molarity. So if you have brackets, that's the same thing as concentration in molarity, moles per liter. So we have this concentration, moles of acid, so we just plug it in. So plug this entire number and you take the log of it. So pH is the negative log. So you're going to get a -6 as your answer, but pH is the negative of it, right? So 10 to the -6 will equal 0.000001, right? So the answer is the exponent, -6, but we don't want that negative number. We want the opposite of it, right? So pH is the opposite of that exponent. So the answer is 6. Here we got the concentration of 0.00823. Same thing, molar. Plug it in, take the log of it. Right? It's going to give you a negative number, but we don't want that negative number. We want the opposite of it. We want the positive. So 2.08. That'd be the negative exponent. See, brackets also means molarity. So take this number, take the log of it, and then remember it's the negative of the exponent. So 2.28. So you should not have a negative in your pH or pOH numbers. It should always be a positive number. Here we're given OH concentration. We need to find pH. So we have to do 2 steps. First, we got to find pOH, and then we're going to use our relationship pH plus pOH equals always 14. Right? So it's a 2-step problem. We're going to find pH indirectly by finding pOH first. Same thing, we just plug this number into, and remember it's the negative of the log, so it's 4. pOH is 4, right? But we don't want pOH, we want pH. Yep, so pH would be 10. So pOH plus pH must always equal to 14. Yeah.
So if that equation was 0.001 grams,
Grams? Oh, okay.
I had that problem on.
You know how to find molarity, don't you? We just went over that. Moles per liter equals molarity, so you have to solve for. So that's the higher level, higher cognitive skills. You know all the steps, you know all the parts, but I didn't tell you directly which ones to use, but you know how to solve for molarity. It's just moles per liter. You know how to solve for moles, right?
Yes.
Grams divided by the gram molecular weight, grams per mole. So all the information's there, you just gotta get to that higher level of knowledge and wisdom. So good question. All right, for E, same strategy. We're given base, so we gotta find pOH first, then indirectly solve for pH. So pOH is 1.28, so pH becomes 12.72. E, same thing. So instead of molar, we got brackets, which means the same thing. So POH is 6.52. pH is 7.48. So for the homework yesterday, a few of you guys, the last few questions, because we didn't go over this for yesterday's assignment, but for a few of you guys forgot to go to pH. You found POH, but you forgot that last step. Corrected gas volumes. So the atmospheric air that we breathe in contains water and water vapor. So water's not going to be involved in exchange. So we're going to have to remove that volume when we're calculating our ventilation. So we'll use the figures on your page, in your book, page 196, to correct. So it's just subtract whatever the vapor pressure is at the given temperature. So if you're not in the desired units, then just convert to the desired units first. All right, so the first one, at 28 degrees, it is the vapor pressure, partial vapor pressure is 28.4. At 36 degrees, it's 44.6. At 20, it's 17.5. And at 16 degrees Celsius, it is 13.6. So I looked up those values for you. And you just have to subtract. So A, you get about 192. B, about 875. For C and D, you have to convert to torr first. So 760 milligrams per atmosphere and 14.7 pounds per square inch for 1 atmosphere. So change into torr first and then do your correction. C, about 819, and D, 762. So you will need to use these corrected pressures when we do the combined gas laws. All right. So as you guys recall, the combined gas laws can be rearranged. So we'll just use this equation. You guys have this in your handout, so you can use that tomorrow. And we need to do corrections and convert to the units we want. So pressures we'll need to correct. Volumes are in mL, so we're okay there. They'll cancel out. Celsius needs to be in Kelvin. So pressure 1's corrected. Temperatures in Kelvin, pressure 2 corrected, and temperature 2 is now in Kelvin. Right? So now all we do is plug and chug. We'll use this equation. And V2, all you gotta do is 712.5 times 125 times 309 divided by 293 divided by 711.4. Should come up with about 132 mLs. So let's see, your pressure went up a little bit, temperature went up a lot more. Okay. Right, the next one, same thing, we got to correct the volumes at the given temperatures. So at 25 degrees Celsius, we got about 23.8 millimeters of vapor pressure. And at 37, we got about 47.1. So they're corrected there. And the temperatures are now in Kelvin as well. mLs and mLs are good. They'll cancel out. Plug and chug. All the terms on top multiply and divide it by the terms on the bottom. The corrected volume, V2, would be 106 mLs. All right, last thing, I guess I'll have to write these in. You guys punch in the numbers for us. So liquid oxygen duration, very similar to H and K and E cylinders. Our conversion factor, depending on if it is measured by pounds. So if it's measured by weight, our conversion factor is 344 liters per pound. 1 pound of liquid O2 is going to give you 344 liters. 1 liter, so this is by volume. So this is by weight. This factor is by volume. So 1 liter of liquid oxygen by volume will yield 860 liters of oxygen gas. Right? So this is liquid. Plug and chug. So for 2 pounds, take our conversion factor times 2 pounds, and then you just divide it by the flow, which is 4. How many minutes would that last?
172.
About 172. For B, we'll do the same. We'll take our conversion factor, 344 times the weight, 3 pounds, divided by the flow, 5. 206. So not too bad. So this was by weight, where we used 344. So we're not going to deplete these containers, so we got to find the difference. So here we got 5 pounds minus 0.5 for a total of 4.5 that we're using. So take our conversion, 344 times the weight, and our flow rate here is 3. 400. How much?
How'd you get the 3, please?
The 3 is here. It's the flow rate. 516. Okay. And then for D, we got to get the 4 pounds. We're going to a 1/4 pound. So we're actually using 3 3/4 pounds. 344 conversion rate times our weight, 375, and our flow this time is 2.5. 516 again? Yeah, about right. 1500 divided by 900. Yeah, that's about right. All right, this time we're going to use volume. So 1 liter volume of liquid oxygen yields this much volume of gas. So capacity, 2 liters times the conversion over the flow rate. Not bad. Here our capacity is 0.8 liters. 860s our conversion factor, and the flow is 3. About 229, 16. Yep, that's about right. It's about 229. All right, I think this is the last one for the review. So here we got the gauge number to contend with, no problem. All you got to do is add that. 1.6 times the conversion, 860, times 1/3. So the container is only 1/3 full, and our rate is 4 liters. So 1.6 times 860 divided by 3 divided by 4. What do you get?
114.
About 114. So 1.6, 16, 5. Yep, that's about right. And for D, same thing. 1.2 liter capacity. Conversion factor is 860 liters. And this gauge is 3/4 full. So you can turn that into a decimal if you want. 0.75. About 387. Let's see. 8. Yeah, that's about right. So the addition is just what the gauge is reading. Add that in the numerator. All right, so that covers all for the course. So part 1 and part 2 from today.